Şimdi Selçuk bizlerle olacak. IoT ve Serverless bir arada. Ben merak ettiğim diğer bir sunumdu. Onu da birlikte izleyelim. Hemen bir kurulup başlıyoruz.
Benimki bağlı, aynen.
Karıştı mı iki tanesi?
Karıştık abi. Bakayım ya. Okey. Oraya gelmedi.
Bağlayacaklar, ayarlayacaklar.
Ha, tamam.
Sen de gel, gözüküyor mu? Gözüküyor.
Bir şeye bakayım. Displays'den kontrol edeyim. Şu an görünmüyor.
Tamam. Doğru.
Yes.
Tamam. Şey dedim sen çalışıyor.
Çalışıyor. Yes. Çalışıyor. Hi. Welcome to my talk. Being a Turkish citizen, I can speak both of the languages, but I want to check if is there anyone in the audience who don't speak Turkish? No? Türkçe'ye dönmemi ister misiniz? Türkçe mi yapmamı istersiniz? Oh, there are some people who don't speak Turkish, I think. Yeah? Okay. Let me keep it English because there are some international guests who traveled just like me from a long way. Today, I'm hoping to give you a new concept to build and you preserve your architecture. And I will try to support this concept with first-hand experience on a high-scale AWS workload. My name is Selcuk Sasoglu. I'm a principal software engineer in PostNL, and I'm coming from the Netherlands. I would like to briefly mention PostNL to you. PostNL is one of the largest logistic companies in the Benelux area, operating in the Netherlands, Luxembourg, and Belgium. To give you an idea about our scale, I prepared this slide. As you can see, we deliver 7 million mails per day, 1.1 million parcels, and our yearly revenue is around 2.3 billion euros. To be able to achieve this kind of operations, we use hundreds of software systems that helps us on the field. And a large majority of these software systems are designed and are running on AWS. PostNL, as a preference, uses serverless technologies on AWS. And we don't even have our own data center. All our software is being executed on the cloud. Today, I would like to tell you about our first IoT platform that we built. And when we first started with this project, we didn't know what to expect from it. And you will see it from my examples in the following slides. But let me first tell you about the problem that we are addressing today. So, long-lasting systems are difficult to design, and they are difficult to implement. They are even more difficult to operate. I'm not talking about like a weekend project for you. I'm talking about enterprise-grade projects where significant investment is being made, and the solution that you're developing has to operate for long years of development. And strangely, change itself is the only constant in our profession. Why? It comes from the tools and the libraries that we're using to help us get faster results. The change also comes from the people who are actually using our solutions. And the change also comes from the community where, like Docker, came in and changed completely how we develop software. So as long as we're building software systems, change will be there. This begs the question, can your system and software architecture survive this kind of constant change? Because this very question conflicts with the definition of architecture, because architecture defines the hard parts that are difficult to change. So, how can you select an architecture that will survive long years of development? How can you embrace constant change? There's also another aspect to it. You spend significant time at the beginning of your project to select the best architecture that will fit into your solution. But how much time are you spending to preserve or protect that architecture? So targeting this problem enters the evolutionary architectures. We didn't invent the evolutionary architecture, but we have been executing one for the last 3 years successfully on a high-load project on AWS. I will try to cover just enough information so that you can understand the concept. But if you like it and if you would like to apply it into your daily work, I would definitely recommend you to buy this book. And second edition is out recently. This talk, I have given it a few times already, but it has been revised according to the second edition. And in the second edition, they added significant number of examples from current times, and also they added evolutionary data, how you can evolve your data together with your architecture. So what is an evolutionary architecture? Evolutionary architecture supports guided, incremental change across multiple dimensions. What does it mean? We will come into more details in the following slides. An evolutionary architecture is not an architectural style like monoliths or serverless or microservices. It is a shift in your mindset to protect the survivability of your architecture for long years of development. Of course, when you are doing that, if you select an architecture that will help you in evolving, it will be easier for you in the long run. An evolutionary architecture approach helps you select and preserve the correct architectural style for your solution. And it lets it to evolve in the direction that you control. And this can be achieved with the help of these three pillars: appropriate coupling, guided change, and incremental change. So let's go into a little bit more detail what these mean. With appropriate coupling, let me give you an example from a monolith. These architectures are also referred as a big ball of mud. And if you have a big ball of mud, independently deployable component is just one. It has highly functional cohesion, so all the requirements that you need to create a new feature is there together with it. On the other hand, your deployment size and the impact of a change is really high. So this system is a little bit hard to evolve because every change you make will affect all the other parts. If you go all the other side of the spectrum, if you look at microservices, your deployment size is really small, but over here you can still make a mistake if you go too granular and if you separate the functionalities that are supposed to be together into different services, you're going to have to deal with difficult problems like distributed transactions. So then the functional cohesion of your services really determines whether you can evolve your architecture or not. So it is really crucial that you find the right coupling of your service that fits your solution. To be able to create an evolutionary architecture, you need to find the right coupling, right functional cohesion that also gives you the smallest deployment size. And this defines the architectural quantum of your architecture. The key takeaway from here is that if your architectural quantum is too big, then your system is probably difficult to evolve. The second part is a guided change. And I think this part is the most important part of this talk. So, adapting evolutionary architecture approach helps you select the correct architecture style for your solution. Here are some key dimensions or some requirements that your solution needs to fulfill. If you look at this list, you will see some of them are familiar to you because you're also doing similar things. And the first thing when you want to execute an evolutionary architecture is to know what are these key dimensions for your solution. Depending on what you want to build, your key dimensions will differ. And this is a continuous process that in the beginning you will have some key dimensions, but as you keep developing, some of them will need it to be added, but some of the irrelevant ones needs to be filtered out. Let me give you an example and you will get easier what I mean. So let's say that you would like to build the next generation IDE. You want to build the next Visual Studio Code. These could be your key dimensions. You want to have an IDE that is really robust and responsive, but on the other hand, you want your users to customize it, bring their own plugin. So when you know that these are your key dimensions, combining it with the knowledge of appropriate coupling, maybe you should select a microkernel architecture. If you do that, you can build the kernel as robust and responsive as possible. On the other hand, as a fitness function, you can check the contracts between the plugins and the kernel, and then the users can bring their own plugins and customize your IDE in the way that they want. This will guarantee a longer period of development for your IDE. These are the key dimensions that we selected for our IoT platform. There's no time to touch all of them, but I would like to mention 3 of them. The first one is reliability. We are working with IoT devices, and they are known to be unreliable. They have network issues, their batteries ran out, they have communication issues. So we have to extract reliable business information out of these unreliable devices. So we had to do something about it. On the other hand, there are different types of IoT devices, and we would like to have the possibility to try all of them. That's why flexibility is important for us. And as I said in the beginning, when we started with this project, we didn't know what to expect from an IoT platform. It was experimental. So we wanted it to evolve in the way that business wants it to evolve. That's why evolvability was important for us. One of the decisions why we selected to execute an evolutionary architecture. So once you know your key dimensions, then we can protect them. We can add guardrails to the highway of evolution. How are we going to do that is something called fitness functions. Fitness functions is a term that's coming from genetic algorithms. Normally it is used to define success. And in a genetic algorithm, what you do is, based on a certain criteria, you spawn multiple instances, and the ones that still fit for survival will survive, and the others will die. Of course, you can't do this for your architecture. You can't spawn hundreds of them and see which one survives. That won't work. So they changed it a little bit, that I know the key dimensions. If I find a way to protect them, I can only let the instances that adhere to my protection, and all the other parts or all the other instances will just die. So fitness functions come in different formats. So it could be, for example, a unit test that, for example, if you're building a layered architecture, the unit test could be checking the calls between layers and make sure that you are not calling, I don't know, database from presentation layer. If you're building an API and response time or performance is a key dimension for you, fitness function could be a load test that fires upon multiple requests for a certain amount of time, and for example, the response time should not exceed a certain period. If we come back to the IDE example, the tests that are constantly checking the contracts between your plugins and your kernel could be the fitness functions. So what I'm trying to say is that, unfortunately, we don't have enough time to go into detail, but fitness functions could be atomic, so you know the result immediately, or they could be holistic, so they can happen after you deploy. But the key difference is that a fitness function doesn't check functionality of your system. They don't care. The fitness functions care about the key dimensions. Whatever the key dimension is there for your system, the fitness functions try to protect only those and nothing else. The last pillar is incremental change. To support evolution, the best approach is to make small iterations, incremental changes. But while doing that, you have to guard your key dimensions using the fitness functions that we just talked about. To facilitate an environment where evolution is possible, you have to give your development teams possibility to experiment. They will make a small iteration like this one, but if it fails your fitness functions, they will have to roll it back. And then they will create a new type, a new version of the system that is adhering to your fitness functions. There will be also other cases where an old system is not fulfilling their purpose anymore, and you will need to run a second version of it in parallel together with that one. So, and there will be iterations coming on the new version as well. So as you can see, there are a lot of deployments over here, and if you don't automate this, you are not efficient. So automation is really key while making small changes. So I don't think I need to mention to you the benefits of CI/CD pipelines, but the CI/CD pipelines are a great place to run your fitness functions, actually. And if they fail, you don't let the deployment to happen. Easy, right? All right. This was the theoretical part of the talk. Now let me tell you about what we have built. The current version of the IoT platform is currently an asset tracking solution. But we know that IoT is not just for tracking assets. We know that we can use IoT for a lot of different functionalities. That's why we have added anchor points in our platform to redirect data coming from certain devices to another data pipeline, etc. But the current implementation focuses on asset tracking. These are the assets that we are currently tracking in the Benelux area. They are called roll cages. They are, as you can see, steel cages that has wheels and capable of moving parcels around. And how do we track them? Each one of them has a beacon under their flat base. And these beacons send out advertisements to their surrounding area at certain times. And if they are not in use, the roll cages are not in use, as you can see, we can stack them together and then move them around easily. This is a picture from our sorting center. As you can see, we're using these roll cages a lot. And why do we track them? Because we use them everywhere, not just in our sorting centers. We also use them in first mile and also the last mile when we are delivering to our customers. So what happens is that when you track them, you can gain a lot of insight about what's happening on the field, and it opens up a lot of possibilities for resource optimization. At the current state, our platform detects 380,000 of these roll cages. If you look at it from a high level, it looks like this. Everything between the dashed lines are in our AWS account, and so they're in our control. Everything outside of the dashed lines are not in our control. As you can see, we have the beacons. Beacons do not directly connect to the platform, but there are gateways in between. Currently, there are 5 different types of them, but you can categorize them in 2 categories like this, fixed and mobile gateways. Each one of them is connected to an inlet on the platform. The inlets do the first validation and allows the detections to pass. From there on, it goes into truthening and aggregation. Before that, to give you an idea about our scale, when we combine the data coming from the inlets, we see 15K to 40K events per second. These numbers are real. I double-checked before I came here. So it corresponds to more than 2 billion events per day. So we have to deal with this kind of traffic with this platform. It wasn't like this, of course, when we started, but we grew up to this point right now. If you check the number of business events we are sending out, it corresponds to 1% of what we are ingesting, actually. And this is happening in the truthening part. That's where the magic happens. That's where our reliability comes in. Because we observe the incoming detections for a certain period of time, and we select the best detections out of it, and then create business events only by using those reliable detections. After truthening, there are state machines. I have added only 3 examples of it. They check what's happening in the current detection, what was there in the previous detection, is there a difference? Do I need to create an event? And then it goes to the outlets. From there, we send it out to the other parts of the company. All right, I'm running out of time, so I need to go a little bit faster. If you look at normally how it looks, it's like this. We have around 22 modules, microservices, that fulfills the entire data pipeline. So let's zoom into only one of them. As you can see, this is one of the inlets that welcomes the incoming detections. It has single responsibility, and as you can see, it's not that big. Because when we try out something, and if it doesn't work well, we would like to sacrifice it. That's why we try to keep all our microservices and modules really small. But this is not how we develop them. We develop them like this. So when we create a new module, we also create test resources around it. Of course, when we're building modules, fitness functions are important for us. So each Lambda has their own fitness functions together with their behavioral tests. So a common example of fitness functions in the Lambdas is that, for example, each one of them have a startup test that will guarantee that that Lambda will work if you invoke the handler function. We are using onion architecture in our Lambdas. We have fitness functions that checks the calls between layers. So you have to adhere to that rule in our architecture. Of course, there are a lot of other quality gates before you can deploy or attach this module to the overall platform. So there are a lot of behavioral tests on the Lambdas and the microservice itself. If we look at the module, we also have sometimes fitness functions that checks a certain key dimension as well. That depends on the microservice or the module, but if necessary, we have them there. One of the common fitness functions in our modules are the contract validations. Because in a microservice environment, the most important thing is that you keep the contracts, the contract schema always the same so that you can collaborate between multiple microservices. So this was an example of appropriate coupling for you. So we try to keep it really small. Now I want to give you an example about how we do the guided changes. For this, we will zoom into another module called availability. When we first started with the project, we noticed that some beacons are connecting to the platform for the first time. And sometimes they were just losing connection. So we needed something like a heartbeat that tells us when a new beacon is available or unavailable. To solve this problem, we needed a caching mechanism. And when you are in a serverless environment, it means that you have to find a solution for distributed caching. That's a difficult problem to solve, at least in the first try. So, as you can see in the first version of that service, it is very simple. We didn't want to do distributed caching because we didn't know enough. So we created an in-memory cache on a Fargate service, and it helped us scale from 10,000 roll cages to 50,000 roll cages, and during that time, it worked pretty well. But this was scratch one for us for a distributed caching solution. And then in geofencing, we noticed that we are sending a lot of events for no reason. And it required us, again, a second time, a caching mechanism. This one, we also solved with a Fargate container, with an in-memory. But this was scratch two. Then we started processing accelerometer telemetry. As soon as that happened, we noticed something new that we didn't notice before. So depending on the gateway around the beacon, sometimes we receive the accelerometer data, and sometimes we don't. So we had to cache it as well to see when is the last time that we have seen the accelerometer telemeter from this beacon. But this was scratch 3 this time. So this was good enough for us. We have observed the patterns in our system to create a distributed cache right now. That's why we replaced the Fargate containers with Elasticache. We knew about how the data access patterns are, how our data should be stored on a distributed cache mechanism. So it was the perfect time to do this. While doing this, we executed the behavioral tests and also the fitness functions at the same time, while putting the old version of the system and a new version of the system together on the platform, and we waited until the new cache caught up with the old cache. So, as you can see, the fitness functions protected the overall system to operate, and also with the behavioral functions, we made sure that we are not losing any requirements. So when the new cache caught up with the old one, we just removed the old one, and with almost no downtime, we switched to the new version of the system. And after each module is developed like this, you still need to put them into the platform in overall. The platform itself also has fitness functions. For example, one of the examples that I've written here is that when we ingress some kind of advertisement, it can not exceed 12 minutes before we send out a business event out of it. So this is always checked with every iteration of the system. So if you make a mistake, the fitness function will fail, and then you will need to find a new iteration of it. All right. So this was it, but let's recap. Quick guidelines. As I said, you are going to make small iterations, and you need to deploy a lot. It's good if you can make your actions reversible. For that, you can try to use feature toggles or use one of the deployment strategies to your benefit. But do not over-engineer to support reverse ops. The second one is defer solutions until patterns emerge. Don't jump into decisions when you first see a problem. Just collect information, see if more patterns will emerge, and only after that, implement the solution, because then you can support all of the patterns that you have seen so far. You can hide the difficult decisions behind abstractions or anti-corruption layers until you find the right solution for it. And then, don't forget to version your services and internal, external events. As I given the example, do not build so big. Build sacrifice architectures, especially when you're not sure if whether it's going to work or not. And for evolutionary architecture, so try to get the appropriate coupling for your solution. If you can achieve a small deployment size with high functional cohesion, your system will be evolvable. Make sure that you know your key dimensions and protect them with fitness functions. And try to work with small iterations and incremental changes, and always use automation for that. So this was it.
Okay, do we have any questions? Sorularımız var mı? I think not. Thank you.
Problem.
Teşekkürler.
Ben teşekkür ederim.